Um, so that's the game plan. We're going to go over the midterm. We'll walk through the solutions. We'll walk through how to think about everything. Hopefully, if you guys had any problems or concerns about any of the problem or questions, just, you can message via chat if you don't feel comfortable talking. You don't need to have your cameras on. You can have them on. If you go to the restroom, leave your camera here. Right, we've all seen those great YouTube videos so far. So we don't want any of those embarrassing moments. After we go over the midterm, we can take a little break, and then we'll dig into modeling epidemics and how diseases can spread throughout a community. And we'll talk about different interventions governments can do to try and stop the spread of the disease, like quarantining, right? So we'll actually build a simple model to show the dynamics of how a disease can spread, and then we'll implement something like making people stay at home to reduce their social interactions to see how much it'll slow the actual spread of the disease. Okay, that's one thing. Another thing we can do is I've uploaded to Canvas the latest version of the COVID data. So on your midterm, I gave you the number of confirmed cases, the number of deaths, and the number of recovered cases from Johns Hopkins University. That data is actually being updated every single day. So the data I gave you guys last Monday is totally stale now, right? Especially when you have a disease that's growing kind of exponentially. So I've uploaded today's data onto Canvas for us. And there's two things I want us to do with that data. One, I want us to make some cool maps so we can see the actual number of diseases by county. And two, we need to figure out basically what's the actual number of cases in a country. So as you guys know, my family's originally from Syria, right? I think last I checked, Syria is saying they have 5 cases. I don't buy that. I mean, I don't buy that. The United States is saying that they have the most number of cases. The United States is also one of the wealthiest countries in the world, actually the wealthiest country in the world. Because of that, I think there's a very strong correlation between the wealth of a country and their actual number of confirmed cases. So what I'd like to do is build a simple regression model to see what's the impact of GDP on the number of confirmed cases. Okay, so this will be a fun little project for us to put together some of the skills you've developed now from all of your model building and from all of the OLS proofs, right? To actually gather some data from a bunch of different sources, merge it all together into one place, and then walk through how to actually get some inference out of it. Okay, so that's kind of the game plan. Any complaints? Is everyone okay with that? Yeah, this is gonna suck. All right, we'll do our best.
So I have a question.
Yeah.
So the inference or the idea that you're trying to connect, it's basically as GDP increases or as countries have larger GDP, those tend to show more cases of the virus, right? That's kind of the pattern that we're trying to map here.
Kind of. Basically, I want to figure out a couple of things. So obviously one could argue that as GDP increases, they have more money a country will have more money to actually test their citizens. If they have more money to test their citizens, then there's a higher likelihood or higher number of confirmed cases, right?
Sure.
Yeah. I have a bigger N, I have more tests I can take.
Yeah.
Alternatively, I can also argue that as a country is wealthier, its citizens are more likely to be more mobile.
Right.
As they're more mobile, they're more likely to spread the disease.
Right.
So the direction isn't entirely clear, right?
Yeah.
But through a regression, we can try and hold a bunch of things constant and see if we control for the number of people traveling in a country, for instance, we might be able to predict the actual number of true cases we expect that country to have given the number of cases everywhere else in the world, right? Kind of a half-baked idea. I'm not going to bullshit you. But we can try and work on it as an actual problem together. And again, the reason why I'm pitching to do this rather than write down some theory and like walk us through it like we would in a normal classroom setting is, I don't know, it's a new teaching style, it's a new teaching method. So maybe we can like code together and work on an actual project together, right? So I think you guys have enough of a foundation now to actually tackle some actual problems.
Makes sense.
Okay. Everyone has not yet turned in their midterm. For those of you that haven't turned in your midterm just yet, there's not much I can do for you at this point. But for those of you that have turned in your midterm, let's walk through the actual exam. So I think I can do screen sharing now. I'll share with you guys our studio. Don't want to share that. Okay, can everyone see my screen right now? Okay. Yes.
Yes.
Yeah, everyone sees my R Markdown file for your midterm?
Yeah, it's good.
Yeah.
Okay. So let's just walk through the actual problems. We can go through this pretty quickly. Okay, so problem one is literally just asking you guys to go back and look up what an estimator is and what are the properties of evaluating an estimator. So it's exactly the stuff we covered in lecture one, right? So this was the really nitty-gritty stuff I spent a lot of time on, even though it's extraordinarily basic, but because if you understand these things, it carries forward into pretty much every estimator, including the fancy ordinary least squares or any other fancy machine learning methods, right? So the first problem is describe the ideas of biasness and efficiency of estimators. Anyone want to take a stab at that?
Like we know an estimator is unbiased if the expectation, like if we're looking at beta hat, then the expectation of beta hat should be just beta.
Yeah, exactly. So on average, if we sample across, as we vary the sample, right, the average value of our estimator that emerges from these various samples we feed in through it should be equal to the population parameter. So that's the idea of unbiasedness or biasness, right? If there is a bias, then the expected value as we repeatedly sample and feed in the data through our estimator is not going to be equal to the true population parameter, right? Okay, how about efficiency?
It has to do with the variance, so we want the lowest variance.
Yeah, so efficiency is a concept that allows us to basically choose or select among different estimators, right? So if we can calculate the variance of an estimator, that is how much, as we feed in different samples through our data, how much do we expect the results of that estimator to change or vary? We want, if we have two estimators that are both unbiased, right? We want to choose the estimator that also has the least amount of variance. That is, it's the most consistent across different samples. Okay. Part B was asking you to just do a generic proof for the average estimator, show that it's unbiased and derive the variance. I'm not going to walk through that right now because you can literally copy and paste it from lecture one, right? There was a lot of problems in the exam where you could have just copied and pasted. I'm hoping you didn't just copy and paste because it's really an opportunity for you to practice more so than anything. So hopefully that's pretty straightforward. Okay. Part C, I asked you guys to basically write a little simulation to show those two things. So we can actually do this really quickly. So let's just, you guys can see my R Markdown file, okay?
Yep.
Okay. So part C, create a simulation where you know the true underlying population parameter. For each iteration of the simulation, you will conduct two draws from a random normal distribution. Random draws from a normal distribution that has a mean of 1,000 and a standard deviation of 233. Okay, so we'll do mu, going to be 1,000. ST dev is going to be 233. The first draw of this small sample of 10 observations, so small OBS is going to be 10. And the second draw will be a large sample of 1,000 observations. So we can create another placeholder large observations, and that's just going to have the value. Okay, so here I'm doing nothing but literally just defining some values, right? You guys see that all okay? All okay? Okay. So we want to repeat this process 1,000 times, where for each process we're going to calculate and store the sample mean. Okay, so num simulations is going to be 10,000. That's the number of iterations. And we're going to repeat this exact process of creating random data and then calculating the mean 10,000 times. So we'll create two empty vectors, small sample mean holder. Will just be an empty vector, so we're concatenating nothing. And we'll also create large sample mean holder, which is also going to be an empty vector holding nothing inside of it. Next, we're going to write a for loop for I in 1 to the number of simulations. First thing we're going to do is actually take the random sample, so small random. Actually, how did I write this? Let's see. Create a simulation with each underlying population parameter. Yeah, 2 draws. So small sample draws is going to be R norm, random normal, how many observations, small observations. The mean is going to be mu, the standard deviation is going to be STDEV. And then we can copy and paste that again, replacing the word small with the word large. Okay, so Francis, you just so happen to be the lucky guy that happened to be on the Zoom screen for me right now. What is the, what's this first line of code doing? Yeah, that didn't work. Okay, anyone, what's this first line of code doing?
That is generating the number of observations from a population. So basically you're telling to draw that will be 10 observations with a mean that you defined previously of 1,000 and a standard deviation of 233.
Perfect. So we're going into a random normal distribution, we're grabbing 10 elements. So like we're reaching into
undefined population.
Yeah, we're grabbing 10 observations from a normal distribution with a mean of 1,000. So it's centered on 1,000 and it has a breadth or standard deviation of 233, right? So essentially it's the same thing. We're just varying how big of a draw we're reaching in and grabbing. In the first one, we're only grabbing 10 observations. In the second version, we're grabbing 1,000 observations. Okay. Next step is repeat this process 1,000 times. After each draw, calculate and store the sample mean. Okay, so we're going to go into small sample mean holder. At iteration I, we're going to store the mean of small sample draws. And we're going to repeat that exact same thing, but on the large draws, and we're going to store those means. Right? So now if we highlight and run all of this code, we'll basically have now 2 vectors, large sample draws and small sample, 10,000. Large sample mean draws, this one, that has 10,000 elements, and small sample mean draws that also has 10,000 elements, right? Okay, plot out the probability density function of each vector of calculated means. So this was essentially asking you to use the density command.
Wait, Haysom?
Yeah.
Can I ask you about when you're storing? So essentially, because our small, like one of the draws was 1,000 observations, but my population is like 10,000. And so when I'm storing it into a 10,000 row matrix, then am I just continuously repeating that 1,000 observations?
Actually, I think I need to go back and look at exactly what you did, because there shouldn't be the population isn't 10,000. Here I'm just saying the actual population, so like an infinite sample, the full thing, right, the mean of it is 1,000 and the standard deviation is 233. So basically I'm saying the true distribution, ignore sample size, just the full thing is centered on 1,000 and has a standard deviation of 233. That's the actual thing.
Okay.
For each iteration, I'm just reaching in and grabbing a small piece of it. So sorry if I worded that poorly, but that was kind of the idea I was going for.
Okay, yeah, because later in the exam, there was like another thing where we make like the empty matrix.
Yeah.
You know what I mean? And so I'm making, I don't know, I'll point it out later, but it was confusing to me.
Yeah, well, that's actually a good, that's a good way to do it. So that's a good thing to bring up. So later on in the exam, I asked you guys to create population data where you create 10,000 draws from each random normal distribution, right? Yeah. And then I ask you to take subsamples of the population data to bootstrap the estimates.
Right.
Yeah. So that one is basically like 2 layers of randomness. Here I'm just saying there's the true population, reach in and grab a small sample. But I'm glad you're
times.
they're related.
Well, so in this case, you're basically getting 10,000 samples, right? That's the number of simulations that you're running.
So it's 10,000 simulations. In
Right.
each of the 10,000 simulations, first we're simulating grabs of 10, second one we're simulating grabs of 1,000.
Right.
And then I'm asking you to basically plot out the density of the small sample. So here's this idea of an estimator. Every time I pass in a different sample to the average estimator, the mean function, I'm getting a different estimate of the average.
Yeah.
Right? And it can vary a lot when I'm only taking 10 observations from the actual population data. So we can see there was actually some of our draws, so 1 out of like the 10,000 draws, where the estimated mean was 700.
It's crazy.
In another version, it was 1,300, right? We know the actual true population mean is 1,000. Now, the vast majority of our sample means that we estimated across the different 10,000 simulations are actually centered on 1,000. And this is the idea of unbiasedness, right? In expectation, or on average, across my estimator, it's going to be approximately correct. Okay. Now, with the large samples, the range is a lot narrower, right? And this also comes directly out of the proof of the variance of the average estimator, right? Does anyone remember what the variance of the average estimator is?
Sigma square over n, if I'm not mistaken.
Yeah, that's exactly it. So it's sigma squared over n. So as our sample size is growing, the variance we get is going to be shrinking.
Gets closer to 0.
Okay, but across both of these, if we take the mean, for instance, of small sample mean holder, it's almost exactly 1,000. And if we take the mean of large sample mean holder, it's almost exactly 1,000. Right, that's the idea of unbiasedness. They're both pretty much exactly right. Okay, and then I think I asked you guys to do, so basically calculate the means like this, also calculate the variances, and then compare those to the theoretical results. Right, basically, as we increase the sample size by a factor of 100, the variance decreases by a factor of like 100 almost. Yeah, sigma squared divided by n, sigma squared divided by n. As n grows by a factor of 100, the variance shrinks by a factor of 100. Okay, that was kind of what I was asking you to get at. Pretty straightforward, right?
Yep.
Okay. Question number 2. This one comes courtesy of Uni.
Do you want me to share the answer key and I can go over it, or you will go over it?
You can go over it.
Okay, let me share my screen.
Okay, I'll stop sharing my screen and you can share yours. Wow, this is pretty impressive.
Okay, I need to pull up the file first.
Okay, while that's happening, how badly have your other classes gone?
They've gone pretty well.
Really?
Yeah.
Is it the host
Finish it, Joe.
disable the attendee screen sharing? Can you allow me to share the screen?
More, make a host. Okay, you're now the host.
Okay. So I think this is the one. Okay. Can you guys see my screen now?
Yep.
Yep. Okay, so this is question 2. And I think in my T session, I already went over all of the estimators. So first of all, I look at some of you guys answer, and I noted that like the question asking to calculate the estimate. So of beta 1 is beta hat 1. A lot of you guys missed the hat on the estimator. So I'm asking for an estimator, so put a hat on it. And so this is a formula that we already went over. So it's just 0.25. Also beta, the estimate of beta 0 is beta 0 hat. And we already know this, right? You guys don't have to go over like all of the derivation of the estimator. You can just apply the estimator, it's fine. And R square is also like just the percentage of a variation of y explained by the model. So it's just the SSE over SST. And that is 0.714. The estimated variance of the error term is just the sum of square error over n minus 1. The degree of freedom is n minus 2, not n minus 1, because we estimate two things in the OLS. So we estimate beta 0 and beta 1. That means we lose 2 degrees of freedom, not just 1. So usually you guys can see like when we say that the estimator of a variant usually n minus 1. But in this case, because we estimate the simple regression, which is beta 0 and beta 1, so must be n minus 2 here. We lose 2 degrees of freedom. And so yeah, it's just 2. And the last one is the variance hat of beta 1. It's not just the variance, because we don't know sigma square epsilon. So that's why we have to use sigma epsilon hat. So that's why the variant is variant hat of beta hat 1. And it just the epsilon, not epsilon, sigma square hat of epsilon over the sum of xi minus x bar square. And that's 2 over 16, 0.25. That's it.
Do we lose points for not putting the hat?
I'm sorry?
Do we lose points for not putting the hat?
I would deduct some point because I think it's important to know what's different between of the population parameter and the estimate parameter in the term of notation.
It's very hard to write those notations. So.
I agree with Uni, but it's not going to be something to like, it's not going to be a change of point that's going to change your grade. Does that make sense?
Okay.
Okay, so the next question is this, the suicide question. And those who already know my research, I study the effect of unemployment on suicide. And so that's why I use employment and suicide for this question. But this is not the regression that I use for my research. So basically, we know that the t-stat is just like the estimate value minus the hypothesized values over the standard error of the estimate. And so because here we're testing whether it's significant, statistically significant or not, which means is it had the effect on suicide. Namely, it's just we're testing the beta. I mean, H naught is beta hat is equal 0 or not. So that's why the hypothesized value is 0. So t statistic is just beta hat over standard error of beta hat. And so, you know, so it's a 3 thing in the, this is formula. And if you know 2, you can imply the third one. So this is the number that I calculated. So I can compare with your answer. And so, okay. And the second question, suppose, what do I test? Okay, so I want to test if it have any effect on the likelihood of committing suicide. And I give you here is 2 critical value. One is at 2.5, and one is 5% significant level. And okay, so the critical value is also depend on number of observation, but like the larger we have, the larger sample we have, it's more approach the normal distribution. So that's why I give you like n is very large and it's greater than 1,000. So this t statistic, I mean the t value is very close to the normal value. And the first question asking for the two-tailed test. So we compare it with t of 0 to 5. And because it's greater than 1.96, we reject the null at 5% level. So, okay, similarly in question C, part C, I asked if it significantly increased the likelihood of committing suicide, which means H1, H naught is still the same, and H1 is beta 2 greater than 0. So the H naught is still a simple null hypothesis, but H1 is a composite alternative, which means beta hat is greater than. And so this is the upper tail t-test, so we compare to 0.05 instead of 0.025. So the whether it's an upper tail or lower tail, it depends on H naught. I mean H1, not H naught. So and so we compare with 0.05, and because t stat is greater than 1.65, we can also reject the null. So if you compare with the wrong t statistic, I mean t value, you guys will fail to reject the null if you compare with 0.025. Okay, so again, this question is just asking whether which t value we should pick for our hypothesis test. And regardless what is the H naught is, we only look at H1 when we find the rejection region. So if the question asking for H naught is beta 2, beta hat 2 less than 0, it's still the same. It's not depends on H naught. The rejection region only depends on H1. Okay, yeah, and that's it.
Just a quick question. Did you say that it depends on if it was the upper or lower tail that we select the t-stat, or wouldn't it just be like if it's, if you're using the terminology, if it's equal to versus greater than or less than?
So technically, you know, those betas are kind of continuous, so we can never ever find if beta is equal something exactly at some point. You know, if it's continuous distribution, the probability of beta equals some number is only 0. So when we conduct the hypothesis test and we decided the rejection region, whether it's a lower tail, upper tail, or two tails, it depends on the I mean, the alternative that we choose, H1. Does that answer your question?
It does. Yeah. I came to the right answer, but I used the wrong thinking.
Okay. Yeah.
There was no part D, right? Just to make sure of that question, because I almost crapped my pants right now when I saw that there was a question on R square.
Oh yeah, that question. Hazen crashed it out, so you don't need to worry about that.
Okay.
Yeah, that's question I wanted to test is like if you guys know is it R square only between 0 and 1? Because like when I do statistics, a lot of people don't know that.
Okay.
So I want to put it there, and Hazen said, "Oh, this is a stupid question." He crossed it out.
I crossed it out because you have it as 1.86, so it's tricky because you have to convert it to a percentage.
Yeah, I freaked out. I thought that I had missed that question.
I know, you're good.
Okay.
And any other question? Okay, I will give it back to Hazen. Okay, how can I stop sharing my screen? Stop share. Okay. On yours now, Hazen.
Okay, so well, you have to make me the host again.
How can I make you the host?
So you have to click on my name, click more.
Okay.
Or here, I can do it. Reclaim host. Got it. Okay, I'm the host now. Okay, so let's just keep going through the rest of this. Okay, so those were questions numbers 2 and 3. So question 4, this was mostly just proofs, right? So recall that OLS, yada, 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 you can write out OLS as actually a matrix, right? So Y would be just a vector. Your X matrix is going to have, it's going to be an n by j or n by j plus 1 matrix if you consider beta 0 as not part of the set of independent variables. But basically the 1 represents the intercept term, right? Because if you take the dot product of this matrix, this X matrix with a vector of betas, the 1s are going to be multiplied by the beta 0s. So basically it's just going to be beta 0. And then our error term, our residual term, is just going to be a vector of residuals. Okay, so here I was asking you to, again, just set up and solve the minimization problem for ordinary least squares using matrices, right? And I asked you specifically that I know you're capable of copying and pasting the lecture notes. Do not do that, right? I want you to actually just practice writing it out. And a couple of you asked me if it was fine to write by paper or to type it out in LaTeX. I told you guys it was totally fine to do whatever way you prefer. Hopefully most of you, I think most of you actually wrote it out in LaTeX, which is good because it's good practice for you. But the key thing is I wanted you guys to explain the steps you are taking, right? And the actual assumptions you're imposing by those steps. So here, if I open up lecture 4, I mean, literally the derivation is exactly here, right? So here is basically talking about the residuals. This is basically our minimization problem. So epsilon prime epsilon is our residuals squared, or it's our sum of our residuals squared. If you were to expand this term, the way you would first expand this term is you would have to basically apply this rule from matrix algebra, where if you're distributing, if you're doing a dot product with two matrices and you're transposing them, you have to basically flip. You have to flip the sign, otherwise the dimensions of the matrices don't line up anymore. So I just wanted you to kind of point that out while you're doing the derivation. So there it is, which is the development of the fact that transpose of a scalar is the scalar. Yeah, so I just kind of wanted you to go through and walk through each of these steps. One of the things that I did not write in the lecture notes that I wanted you to think about a little bit is in this step in particular. So as you're going through the derivation, you end up at this step, right? X prime x hat beta or beta hat equals x prime y. This is after you take the derivative and set it equal to 0 and move over one of the terms, you end up at this step. Okay, at this step, and basically you have to take the inverse of x prime x in order to isolate beta hat. That's the only way you can move this term over to the right-hand side. Okay, when you do that, you're making an assumption about what x prime x is. You're making the assumption that x prime x is itself invertible. Some matrices you can't take the inverse of. Okay, one of the core assumptions behind that is basically we're saying that x prime x has to be full rank. Or more precisely, x has to be full rank. Okay, what does full rank mean? Anyone?
There is no multi-collinearity between independent variable.
Yeah, exactly. There's no multicollinearity. That is, no two columns or no column in X can be a linear combination of the other columns in X. Right? Okay, that's sort of the key condition in order for us to invert that matrix. So those are kind of the core steps there. Part B, so suppose we have the following data generating process, y equals beta 1 x1 plus beta 2 x2. Under this process, is the mean of the residuals equal to 0? Explain your response. What do you guys think?
I think it will not be 0 because we don't have any intercept in that model.
Exactly. So again, going back to lecture 4, right? If you literally just scroll down a little more, you can see that at that step, where instead of actually plugging in or taking the inverse of x prime x in order to isolate beta hat, if we didn't do that, if instead we substitute in for what y is, that is, we plug in for y, which is really just x hat beta, or x times beta hat plus epsilon, if you just plug that term in terms of y, you'll actually get to this step. And then through some distributing some terms and through some simplification, you'll end up at x prime or x transpose epsilon is equal to 0. Okay. The main reason that we have x prime epsilon equal to 0, or so x prime x or x prime epsilon doesn't necessarily tell us the residuals are 0, okay? The reason why we know the residuals are 0 is if we do, actually here, maybe I can write this out. Let me try sharing a different screen. Stop sharing that screen. Let me share that. Now we're getting fancy. Okay, so the term I just pointed out in R, right, or in the R markdown file was 0 is equal to x prime epsilon. Okay, the question is asking if we remove the intercept term because there was no beta 0, is the mean of the residuals going to be equal to 0, right? So if we think about what X is really the matrix of all of our predictors, right? So we have basically the first column is a bunch of 1s, everything else is all of our X's, right? X1, 1, X1, 2, yada, yada, yada. Yeah? Yes, okay. X transpose is literally basically just the flip of this. So X transpose, so this will be equal to X. X transpose is going to be basically having our 1s, or that first column here is going to shift and become the first row here inside of X, right? Okay, so if we do X transpose then times epsilon, going back to this term, the first result of this dot product is going to be basically a vector of ones, right? 1, 1, 1, 1, 1, being multiplied by a vector of epsilons, epsilon 1, epsilon 2, epsilon 3, all the way up to epsilon n. Yeah. The first term here is basically saying 1 times epsilon 1, epsilon 1, plus 2 times epsilon 2, plus the same pattern is going to continue. So basically we're adding up all the residuals, right? If we're saying that x prime epsilon is equal to 0, we're basically saying that entire matrix resulting from that dot product. How do I erase stuff? I don't know how I can erase stuff. I'll scratch it out instead. Okay.
I think it's at the bottom, the eraser.
Wow. Cool. I'm learning something new today. All right. So the result of this 0 isn't really just a 0, right? It's actually a vector of zeros. So really another way of writing that is like with a little arrow on top of it, for, I guess depends on your mathematical background, but a 0 with a little arrow over it's like it's a vector of zeros, right? Which means it's not really just one number 0, it's actually a bunch of zeros. In fact, it's j zeros. It's for every single, or n zeros, for every single residual term, or for every single row inside of this matrix X times epsilon, it's going to be 0. Okay, so when we say this first element here is 0, we're basically saying the sum of the residuals is equal to 0, right? We know then that the definition of a mean is really the sum of all the observations divided by n. Well, if we're saying here the sum of all the observations is 0, it doesn't matter what we divide it by, it's still 0. Okay, so this question then is essentially saying if we don't remove if we do not have an intercept, we're not basically guaranteeing that the residuals are going to be on average 0. Okay. Yeah. For question or part C, derive the general form solution for the variance of the OLS estimator, right? Our good old sandwich. Keeping the term, the expectation of epsilon, epsilon prime, conditional on x. Derive the variance of the OLS estimator under the Gauss-Markov assumptions, and then derive the white heteroscedasticity robust variance estimator of the OLS estimator, right? And then I ask you to describe the structure. This comes directly out of lecture 4. Basically, the key thing is, under the Gauss-Markov assumptions, we're explicitly stating that this term is equal to what?
Be 0.
Sigma squared I.
Sigma squared I. We're assuming that this term is exact, it's homoscedastic. We're assuming that every single term along our variance covariance matrix of the residuals is going to be the same. It's going to be sigma squared I. Okay, so again, if we go back into lecture 4, that's the assumption under homoscedasticity. All right, so when I ask you to describe the variance covariance matrix, I'm asking you to describe this condition. Okay, so if we go into the sandwich estimator, which was here, nope, a little too far down. If we go into our sandwich estimator, this thing, you can plug in for this term, the expectation of epsilon, epsilon prime conditional on x, you can plug in for that simply sigma squared I, which is really just a constant term, so you can bring it forward, and then a bunch of stuff is just going to cancel out almost immediately, right? Basically, all of these terms will cancel out. X prime x will be canceled out with x prime x inverse. So then you're just left with sigma squared times x prime x inverse, which is a huge reduction in the calculation of the variance, right? Okay. Versus with the sandwich estimator, so this was the white paper, we're assuming that, or basically he was able to show that a robust estimator of epsilon, epsilon prime, or an unbiased estimator of epsilon, epsilon prime conditional on x is just going to be plugging in epsilon, epsilon prime. So basically you can't do any further simplifications. This becomes the variance covariance estimator. Okay. Okay. What's the difference between the resulting variance covariance matrix here versus the variance covariance matrix here? What's the difference? Do they both have zeros off the diagonal? Yes, they do. They both have zeros off the diagonal.
It's just the you're not assuming that the variance is constant diagonally. Basically, you're allowing that to change or be different in a way.
Exactly. I'm allowing the variance of each estimator, or each, like the variance of beta 0 to be different than the variance of beta 1, the variance of beta 1 to be different than the variance of beta 2, etc. I'm allowing it to vary. Okay. Versus under homoscedasticity, everything has the same variance, which is a pretty strict assumption. Okay. The reason why I'm being really annoying about this is all of the default statistical software is just going to give you the Gauss-Markov assumptions version of the standard errors. You need to know that as econometricians. Okay. That is, the default statistical software results are going to be giving you the version that's assuming that there's the same variance in the variance covariance matrix. Okay, that's going to cause a lot of problems when you're doing statistical inference, because people are just going to be like, no, that's wrong. All right, so if you go and present at a conference, pretty much everyone's always going to attack your standard errors, right? I think Uni can talk about that. Uni, what was your experience like? Did everyone just assume you did this correctly?
I'm sorry?
Did everyone just assume your standard errors were correct, or did anyone nitpick you when you presented in Florida?
No one talked about it. So I just
No one
tell
talked
them
about it?
my variant is a bootstrap standard error. And they say, okay.
Okay, fair enough. So
With that,
another version of calculating standard errors is a more flexible version, which is the idea of bootstrapping, right? So remember when we talked about confidence intervals? Yes, we said we could empirically try and calculate the variance of our estimator by just repeatedly sampling and seeing how much the estimator varies. That's the same idea with, you can apply that same concept of bootstrapping to ordinary least squares, right? And I think that was another problem on the exam. Okay, but before we did that, there was another question that asked you to write a function R that'll take in the variable y and x, where y is a vector containing a dependent variable and x is a matrix of independent variables. Each column is a different independent variable. Your function should return a table with the following information. Okay, and then here I wrote some code to get you guys started on writing that function. So let's write this kind of quickly. Okay, column 1 is going to be our beta hat. Column 2 is going to be our standard error beta hat under the Gauss-Markovs. Column 3 is going to be standard error beta hat under the robust white sandwich estimator. Column 4 is going to be t-statistics, and so is column 5. Okay, so first thing we need to do, we need to get our beta hat, right? Well, here I already added in some code for you guys to add in a column of 1s for the intercept term. So we can get our beta hat by using the closed form solution you derived in one of the previous problems, right? So the solution for beta hat we know is what? I thought you guys all got this tattooed on you.
Yeah.
Okay, the solution is always x prime x inverse x prime y, right? Okay, so this inverse part, that inverse part is the solve function in R. Solve will take the inverse of a matrix. Okay. To transpose a matrix in R, we use the T command, transpose of X. To take a dot product in R, we use the %*%. So this here, solve of T of X, %*%X, this is solve, or this is X prime X inverse. X prime X inverse. Okay. This itself is going to be dot producted with X prime, or not X prime, transpose of X dot producted with Y. Okay. So that'll return our estimated coefficients. all of them. Okay, for whatever matrix X and Y we pass in. Okay, next step, derive the standard error of beta hat under the Gauss-Markov assumptions. Okay, well, the standard error of our Gauss-Markov assumptions requires us to calculate the variance of the residuals of our model, right? The sample variance. So given that this is our beta hat, or our vector of betas, we can get our predicted y pred, and that's just going to be x, or transpose of x dot producted with, actually it's not even that, it's just x transpose beta. X dot product beta. Okay, so this is going to give us, for each x, it's going to take the dot product with beta hat. That'll give us our predicted values, so our y hat. So instead of y hat or y pred, we can call that y hat. Our residuals are therefore going to be our true observations y minus our y hat, our predicted values. From there, we can get our estimated variance. The variance of our residuals is going to be the variance of the results predicted, right? Or you can actually write it out as the sum of squares divided by the length of the residuals minus 1. Okay, so at this point, it's probably a good idea to like take a breather and see if it's working correctly in our function. So we can see where we can create a data frame that has our beta hat terms and our standard errors. Actually, this isn't complete yet. The standard errors under the GMA are going to be the variance of the residuals multiplied by x prime x inverse, that term. Specifically, this will give us the variance covariance matrix. So when you take the square root of the diagonal terms of that variance covariance matrix. I'm moving a little quick, but hopefully this is like kind of familiar-ish now. Yeah? Does anyone have any issues with this?
So far, so good.
Okay. So what we can do to actually test out our function to see if it's working is we can just make up some data, right? So I'll make y as r norm, or I'll make x1 as r norm 1,000, or I'll do 10,000 draws from a mean of 100 and a standard deviation of 12. Totally making this up. Y is going to be 210 plus x1 plus a bunch more random noise. Okay, so the true estimated, or here, I'll make it 0.8 so we can actually see it. That's my true population model. Okay, so if I run LM using the base R function, that gives me the estimated intercept of 210 and a coefficient, or beta 1, of 0.8. If I use this little function I wrote up, if it works properly, I feed in a vector of y's and I feed in a matrix of x's. Whoops, it's expecting a matrix going in. So I can do as matrix. Is that going to give me the right dimension? It is. There we go. So now I'll have my estimated coefficients and standard errors using our function. Okay, so the results from R, we can do summary LM of x on y. There they are. So these are the results that R gives you. That little function we just wrote up in under 5 minutes. The results of it are here. Beta hat is 209.9908, 0.7999736. Those are the estimated coefficients. matches perfectly with what R is doing. Our estimated standard errors also perfectly match what R is doing as well, except R is actually doing some rounding. So far we're on the right track. Okay. The next thing I asked is I want this function to be a little better than R. I want it to actually return for me the white standard errors as well. Okay. Now we know the white standard errors. We derived the formula for that. It's easier to break this up though into a couple of steps. So remember our sandwich has two components. It has some bread. The bread is this X transpose X inverse thing. It has some meat, which is going to be X transpose our residuals, dot producted with our residuals transposed. Let's see, am I getting that right? Bread, transpose X, diagonal the residuals. Yeah, that should be right. Okay, so then our white estimator is going to be our bread, dot producted with our meat, dot producted with our bread. The standard errors then are going to be the square root of the diagonal of that resulting covariance matrix. Okay, so we can verify that now. Non-conformable arrays, joy. What did I do wrong? Transpose of X, the diag of the residuals squared. That's the same thing. All right, that's fine. Let's go with the code. I'm not seeing what I'm doing wrong, so let's go with this for now. What's going on? Uni, save me.
I'm checking. I think we have this issue before, right?
We did. Transpose of X, dot product of the diagonal, the residuals predicted. Is
It
non-conformable.
should be numeric.
What is it?
Try residual product predicted as numeric.
It's 1,000 by 1. This should be the epsilon prime. There we go. Okay. I guess I wrote it wrong the first time. There it is. So this is basically here is where we're plugging in the epsilon prime as the estimator for the variance rather than plugging in the sigma squared I. Okay, so then this should work fine. So now our estimated standard errors from white are actually way smaller than the standard errors coming out of our Gauss Markov assumptions. Seems too small. Square root of the diagonal, yada, yada, yada. You can apply a sample size correction. It's not going to make too much of a difference, given our sample size. We can verify the results using the sandwich package. No, the results are way off. Solve X transpose X. Transpose X. These should be exactly the same thing.
I had the same problem in the midterm.
Oh, here you go. If I'm getting it wrong, everyone's getting it wrong.
So what I
expect
did,
you guys to be better than me.
so what, so what I did was the residual predicted is as numeric y minus y hat, and it solves the problem.
Yeah, okay, yeah, sure. Oh, still way off.
Up B.
Okay, I'll fix it. I'll fix this, and I'll upload the solutions to it a little later. Well, I'm going to upload the solutions for the entire midterm probably a little later today, and I'm hoping to have everything graded by the end of the week. Yeah, so the code implementation should just be exactly x prime x inverse, x prime epsilon epsilon prime, x prime x inverse. So I'm doing something off that I'm not seeing.
You are missing an S up there on the meat residues.
What am I missing?
Up there is, when you are coding meat, at the beginning you are missing S somewhere. Up there, not here. Go up, there is somewhere meat residue, you miss S. At the end, residue, somewhere, no, up. Meat residues. I've seen missing.
I might have fixed it.
Beat the line.
Somewhere. Meat residue. You can search for meat residue. There is one with no S. I saw it. It is okay. This is okay.
Yeah, something's off. All right, I'll deal with it later. Rather than burn our precious Zoom time together. Okay. Anyway, question 2 or question 5, the last or almost last question, was asking to essentially create some fake data and then use the function that was created up here. You know, but I expected you guys to be better than me. The function created up here to basically see if you can recover the true underlying model from the synthetic data that you generate. So basically, I gave you a true data generating process, and I gave you basically how to create each of the individual terms that feed into the data generating process. And I asked you to basically just make all of your data in step 1. So we can do that pretty quickly. So we'll create num obs is 20,000. Am I losing you guys?
No, you're good.
Okay. Alpha, are you still with us? Okay, so that'll be our number of observations, 20,000. X1 is going to be simulating draws from a random normal distribution with 20,000 observations. We're going to have a mean of 32 and a sigma squared of 12. So the standard deviation is the square root of 12. X2 is going to be R norm num obs. The mean is going to be 71, and the standard deviation is going to be the square root of 21. X3 is going to be also draws from a random normal distribution, but it's going to have a mean of minus 43 and a standard deviation of the square root of 5. And our error term is going to be, or additional noise we're going to tack on, is going to be also draws from a random normal distribution with a mean of 0 and a standard deviation of 14, or square root of 14. Our y data then is 98 plus 21 times x1 plus 8 times x2 plus 89 times x3 plus the error term. Okay, so the question then asks you to combine all of your data into a matrix. So y is going to be, or all data is going to be C bind y, x1, x2, x3, x4, or yeah, just x3. Okay. Take a subsample of 5,000 rows of the matrix created in part A. Now use the function you created in part D of question 4 to estimate the OLS in the subsample. How do the estimated coefficients compare to the true data generating process? Okay, so basically, we have 20,000 possible rows. We want to sample 5,000 of those rows and then feed those 5,000 rows into the OLS estimator function up here. Okay, so we can create a sample index that is just a vector that's going to contain the rows we're going to select out of the full 20,000 using the sample function. So sample, again, will randomly select elements of a vector. So our vector is going to be 1 to n row all data. So 1 to 20,000. We want to grab 5,000 elements from that. So sample index, if we preview it, just tells us the row numbers that were selected. So it just picks for us 5,000 random rows. Okay, so then our selected y is going to be all data first column, sample index. So basically we're grabbing all of those rows for the first column, and our selected x is going to be all data sample index columns 2 to n col of all data. Does this make sense? So take a subsample, take a sample of 5,000 rows, subset out using the randomly drawn index, get the y's, get the x's. Okay, and I'm storing them as 2 separate objects for a very particular reason. By separating out the y's and the x's, we'll have the data in the right format to feed into this OLS estimator function, which expects y and x as 2 separate elements to go in. Make sense?
Should we assign the seed for this part?
Yeah, so I already did that up here for you. Set the seed to 1, 2, 3. So as long as you kept going, the sequence should be fine. It shouldn't make much of a difference. selected Y, selected X, and then even though the data, we know the white standard errors are wrong, there's the estimated results. Okay, how do these results compare to the true data generating process? Well, they're pretty close, right? 98, 98, 21, 8, 89, 99, 27, 89. Pretty much spot on except for rounding error, right? The intercept is a little bit off, but pretty close overall. Pretty straightforward. Yeah.
I have a question.
Sure.
Should you take it as a standard practice to use the robust estimator rather than using what we already know, what it's as default under the Gauss Markov assumptions, or should you just use it when you suspect that there is heteroscedasticity in the error terms?
Remember the idea of efficiency?
Mhm.
Okay. The Gauss Markov assumptions are more efficient than, so imagine if there's like a variance around the variance estimator. The estimated variance of the Gauss under the Gauss Markov assumptions is smaller than that of the white standard errors. So you should use the Gauss Markov assumptions. Most of the time, though, the data you're dealing with is going to be violating it.
Yeah.
Okay. And there's tests for that.
Yeah.
So one of the tests we talked about was plotting out the residuals. So this was the idea of I'll plot my predicted values against the residuals, and I'd expect the term to look kind of constant.
Yeah.
If the residuals are fluctuating in any one direction, right, that means the values of the residuals or the variance of the residuals is not constant. It's changing depending on the predicted value.
Gotcha.
Okay.
Thank you.
Yeah. Any other questions? No? Okay, well, the last question relating kind of to OLS before getting into all the COVID stuff was creating an empty matrix of dimension 1,000 by 4, write a loop that has 1,000 iterations. In each iteration of the loop, take a sample of 1,000 rows of the matrix you created in part A, use the function you created in part D of question 4 to estimate the OLS on a subsample. So basically, I'm asking you to plot out the distribution of the coefficients while using bootstrapping. So a third way of calculating standard errors. Make sense? So standard way is under the Gauss Markov assumptions. Second way is using a robust covariance matrix using the white standard errors. And the third way is by just doing bootstrapping, taking random subsamples, and every single time you do a subsample, record the estimated coefficients. Okay, so we'll create an object called empty matrix, and it's going to be a matrix filled with missing values. It's going to have 1,000 rows and 4 columns, exactly as the function or the problem tells us to create, right? Okay, now we're going to fill this matrix. The way we're going to fill it is by going for I in 1 to n row empty matrix. So for 1 to 1,000 iterations. The first step we're going to do in that iteration is we're going to take a subsample of 1,000 rows from the original data. Okay, so this code we did up here, I could literally just copy and paste it into my function or my for loop. And instead of taking a sample of 5,000 rows, I'll take a sample of 1,000 rows. So again, here we're going to create sample index that's going to go from 120, the vector of 1, 2, 3, 4, 5, 6, all the way up to 20,000. It's going to randomly select 1,000 elements out of that vector. It's going to use those randomly selected elements then to select out the Y variables and also select out the rows inside of the X matrix. It's then going to feed in the selected Y data and the selected X data into the OLS estimator data or function. That thing is going to return our estimated results we want to store the estimated coefficients, which are here inside of the first column, inside of each row, the ith row of the empty matrix results. NANS produced. Weird. Okay, so here, if we scroll through, we'll see every single time the simulation was done, there was, I'm pretty sure the NANS is related to the white standard errors. Ignoring that. Every single time the simulation was run, we get basically a different estimate of beta 0, the intercept term, a different estimate for beta 1, the coefficient on x1, a different estimate for beta 2, the coefficient on x2, and a different estimate for beta 3. Okay. Why am I making you guys do this like 7,000 different ways? Because I'm cruel? Because I really like talking?
I mean, I think you start noticing some of the differences that you have in the standard errors given the method that you use, which is important because the standard error is what you use for testing hypothesis. So if you use a different one, you might end up like rejecting the null hypothesis because you use one standard error instead of using one more accurate, or which one that will be better suited for the type of data that you have.
That's exactly it. But really the whole point I'm trying to drive across is it's very easy to just abstract from the idea of what an estimated coefficient is. It's beta 1. R said it's beta 1. Stata said it's beta 1. Whatever other language said that's beta 1. That's just one estimate. In reality, the beta thing you're estimating has a distribution. Right? We're summarizing the distribution when we look at the standard error. That tells us about the breadth of the distribution. But in general, the beta hat you're estimating isn't a single number. It's actually a distribution of numbers. Okay? By bootstrapping, we're basically empirically trying to simulate what that distribution looks like. And that's what this question was getting at. By storing each of these different coefficients, what we can do now is basically plot out that first column, or the density of it. Or another way of doing this is we can make a histogram of the first column. What did I do? There we go. And that'll give us basically a visual depiction of how frequently or what the range of our different values of beta hat look like. If you take the standard deviation of that thing, that's another standard error. Right? And it's a very flexible one. You're not making any assumptions at all about the structure of the standard error. Okay. So then I ask you basically compare these results to the GMA results and to the white standard error results. In this case, because there isn't much, there shouldn't be much of a difference. There shouldn't be much of a difference because we're dealing with data that's random, normal. We're dealing with a very well-behaving residual term. Really, this is the core thing. Because we created this error term here, epsilon, as normally distributed and having a constant variance, right? They should all look basically the same. The times where this isn't going to look the same is when the error term is basically correlated with x1 or is correlated with x2 or is correlated with x3. Then you're going to have some different issues. Because then if you go back into the definition of the sandwich estimator, when you take this expected value of epsilon prime or epsilon prime conditional on x, that thing doesn't decompose anymore. You can't just say it's sigma squared I. The only way you can actually assume it's sigma squared I is if you're imposing this very strict restriction of there's no relationship whatsoever between the x's and the residual terms. There's no correlation at all. That's what allows us to break up this term, right? So I know we're covering a lot of things, but they're all related to one another. Hopefully that's becoming a little more clear now. Okay, so that was kind of the point of these questions. The last question is more of a fun question, and it's kind of something it's kind of a question I felt like we have to be a little responsible and use our skills to try and analyze the world a little bit. Okay, what do you guys think of this last problem?
It was good, but hard.
Yeah. Yeah.
What are you guys talking about? This should have been easy.
Of course.
Okay. Did you
I don't
guys
know, the grep function was kind of confusing.
Well, what was kind of confusing?
Grep, using grep was like trying to figure out how to use it properly was kind of hard.
Okay, good. The data structure is hideous.
Oh yeah, too.
Right? That's how you know it's not an econometrician that made this. The data is not made in a way that's like very friendly to work with. But so one of the first individuals or one of the first places to basically compile data for COVID was actually Johns Hopkins. So here I included a link for you guys. I think I have to stop share. And then I think I have to, let me close out some things like bank accounts and whatnot. And then I can share another screen. Okay, so here you guys can see yourselves now. Okay. So this link I gave you guys, can you guys see my screen now? All of it? Yeah?
Yes.
So, wow, okay, that's growing even faster now. So this link I gave you takes you to this really cool dashboard that's been put together by Johns Hopkins University. Okay. And what they did is they basically built a bunch of web scrapers to go to all of the different counties in the United States and to basically collect how many cases they're reporting. Okay. So as of today, there's 775,306 cases across the globe of confirmed cases. Okay, what is a confirmed case?
Someone who tested positive?
Someone who tested positive. Right? The key thing is tested positive.
Yeah. Yeah.
Okay. Apparently Africa is doing a very, very good job at not having coronavirus.
Or not testing at all.
Or where?
Or not
Maybe
testing.
they are not testing.
Yeah, maybe they're not testing, right? Or here's my lovely country of origin, where we have 9 confirmed cases and 8 active cases. Okay.
Which is that?
We should learn from them, right? They're clearly managing the crisis very well.
It's the heat.
It's the sure, it's the heat. It's snowing in Syria right now, but all right, sure, it's the heat.
Even if China, it's not believable.
I don't know, that seems pretty bad.
Yeah, no.
Okay. One of the problems we're running into is here we're dealing with the idea of confirmed cases. Okay. In order to get a confirmed case, someone has to be tested. I'm sure many of you have probably thought to yourselves, I'd like to be tested, right? You know, as of late, you've been feeling like, I don't know. I went out for like 2 minutes to like, you know, get some bread. I think that guy might have coughed on me. And now you're sitting at home and you're like, you know, maybe I might have corona. You call up your doctor and your doctor's like, shut the fuck up, stay at home. No, I'm not testing you. Okay. That restriction is happening everywhere. It's actually very difficult to get tested. Okay. It's very difficult to get tested because we have a shortage of tests. And we only want to test people we really think have the disease. Now, given your guys' statistical training as of now, remember how we beat the crap out of this idea of random sampling? Is it a good idea to not be random sampling? If we're trying to learn about the disease,
Well, you're talking about random sampling when it comes to testing.
Yes.
I think in this case, to help, I think for research and to help cure this, then we shouldn't random sample. We should actually sample or test people who are more likely to have the disease.
But then we're not doing any random sampling anymore. How are we making assumptions about the overall population? The whole idea of random sampling is I take a bunch of random draws from the population and I can use that to make some general inference about the total population, right? So for instance, if I were to go back to the United States with all of our lovely little dots, and here's our great little Los Angeles. Okay, here's LA. This is telling me there's 2,136 cases in LA. Okay, so that's telling me a very, 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 very tiny fraction of the population has tested positive for corona in LA, right? What does that tell me then about the overall likelihood of someone having coronavirus in LA? Doesn't tell me anything, right?
Yeah.
What I would need to make inference about any random person in LA is I need to go out and test maybe 1,000 people randomly and see how many of them are testing positive.
Yeah.
No?
Yeah.
Well, this would be if you're accurately trying to deduce how many people had the disease, right?
Yeah.
But
That's
I mean,
exactly it.
Wouldn't doing that also potentially infect more people? Like just having everybody come to a booth to get tested or whatever?
Yeah, absolutely.
Maybe drive-through. Maybe
Or even a
they-
drive-through. Well, now they're doing self-swab, right?
Yeah.
But yeah, so there's a huge human crisis. This is the balance of, okay, we're humans and we're statisticians, right? That's a thing. So because of that, we have a trade-off we have to look at. We have to look at, okay, we have only it's a limited resource. It's actually a precious resource now to conduct a test on someone. We can't just go out and test everyone. Okay, because if I test this person, that could be someone who I end up turning away from a hospital, ends up dying and infecting 1,000 other people.
We are really getting good death rate.
That's tricky in and of itself too. Because here we have basically, in the US, we might be getting good death rate data. But the truth is, I mean, how many people died between January and when we actually started testing for this thing pretty robustly, like 3 weeks ago or 2 weeks ago, that we didn't test for coronavirus? Or rather, are we testing all dead people for coronavirus? I don't know that right now.
I think so. And then also the symptoms are different as everyone. So fever and cough is not present for everyone. So you have it, you don't even know it.
A lot of people have been saying that, but at the same time, I've been having a very hard time. So I've been trying to think to myself, okay, how can I help my society? I'd like to have a lot of data, right? With a lot of data on every single patient, I can try and build a regression to try and see, okay, what are the factors of someone having the disease or not? Right now, we're just relying purely on the government to tell us these are the symptoms or these are the factors. But in reality is they haven't made the data very readily available for everyone to just go in, download it, and try and build their own models to try and predict what's the likelihood of someone having the disease, right? Also, the data is only available at the county level. They're starting to release the data at the city level. Like 3 days ago, I think they announced they're going to be releasing the data at the city level. But at most places across the US, they're only releasing data at the county level. So one of the things we're going to talk about is something called the spatial autoregressive model. In the next two or 3 weeks, we're going to do a day on mapping. So I'm going to teach you guys how to make cool maps like this. But one of the things you can actually do with spatial data is, given the characteristics of my adjacent counties, how does that influence my county? Okay, so I ran a spatial autoregressive model for all the counties in the United States. basically I looked at how many cases does all of the adjacent counties have? How does that impact the number of cases I have? So basically, what's the spillover effect? Okay, and I was able to estimate that for every for every neighboring county, whenever they see an increase of 5 cases, that's going to spill over into my county as one additional case. My additional case that spills over is then going to contribute to a 0.2 unit increase in the number of cases in that county. The effect keeps spilling over, right? Because as one increases, the other one increases too. Okay. Nonetheless, there's pretty good data available now, right? So this is the county level data available from Johns Hopkins. So what I asked you guys to do in R was to basically look at this data, the time series data for deaths recovered and confirmed. And I asked you to look at basically a bunch of different states. Basically coastal states versus states in the middle of the US. Okay. And then very fortunately, I don't know if you guys caught it, there's a bunch of articles published all over the weekend. Like the main one was like the New York Times wrote an article saying the COVID is now spreading to middle America. Oh no, right? The Republican base is actually getting hit now with coronavirus. Okay. So here I asked you to load in this data, and I basically wrote the code for you to do so. So I asked you to describe the difference in the curves across the 6 states. And I wanted you to look at confirmed cases, recovered cases, and deaths. So the states that we're going to be looking at are California, New York, Washington, Oregon, Texas, Montana. Okay. So for confirmed cases, what we can do is do a word search, right? So if we preview the data, head confirmed, we can get a sense of the structure, okay? The way this data is structured is you have the province or state as the first column, you have the country or region as the second column, you have the centroid, latitude and longitude, that is the center of the polygon of that province or state or country or region. And then here you have a running time series that gives you the cumulative number of confirmed cases. Okay, cumulative number of confirmed cases. So the first thing we want to do is, well, California is not a country or a region. It's a province or a state, right? So if we go into the confirmed cases, we can search for the word or the first state, states. One, we can search for that word inside of the confirmed province column. And we can use this additional column or flag of confirmed case or ignore cases equal to true. And that'll basically let us ignore any capitalization or weird spelling mismatches that occur because it's trying to do a perfect match. Okay, so here it's saying there's one match. Perfect. It's column 101. Okay, how about state 2? For New York, there's actually 2 results. There's New York and there's New York County. Okay, well, if we click through the data, is there any differences between the numbers? Yeah, there's some pretty big differences. Okay, so for New York, we only want the first result. Okay, so CA or state rows. Okay, going back to California, if I ran this code again for California, it was row 101. For New York, when I do this grep or word search again, it's giving me the results 100 and 320. We want to use result 100 because we just saw that the second row 320 is New York County. We don't really want New York County, we want all of New York. Okay, let's look at Washington. Washington also has 3 results. There's Washington the state, there's Washington DC, and there's Washington County in Oregon. I only want Washington, so I'm going to go with element 99. Okay. How about the fourth state? The fourth state is Oregon. There's just one Oregon, so we're just going to use entry 109. And then we have Texas. There's only one Texas, row 110. And there's also Montana, which is row 149. Okay, so this was kind of annoying, but this is actually the state of the data that we're dealing with, right? They have some counties, they have actual states. It's kind of all over the place. So you need it to kind of just go through and check and do a search to make sure you're finding the right data. Okay, so these are the actual rows that we want to use. 101, 199, 109, 110, 149. Those will give us the data for those specific states. Okay, the data sets do line up. So if I go into deaths and I look at those state rows, it should be exactly the same. California, New York, Washington, Oregon, Texas, Montana, and the same thing with recovered. So they did actually a great job at that. California, New York, Washington, Oregon, Texas, Montana. Lines up perfectly. Make sense? Okay. So the point of the question was, I wanted you to compare the different states. So plot out their confirmed cases, plot out their deaths, etc. So we'll start off with confirmed. So we're going to go into confirmed. We're just going to look at the first state for now, so California. Okay, so the way the data is structured is province, country, latitude, longitude. So the first four columns are meaningless. What I actually care about is the data from columns 5 onwards. So from 5 to the total number of columns that are confirmed. Okay, that's going to return for me this matrix. I don't want the matrix, I just want the data. So I'm just going to call it as numeric. Or I'm going to coerce it from a matrix to just a vector of numbers. And there's my vector of numbers, or the vector of confirmed cases in California. Okay, so case data. Now, each one of these numbers corresponds to a particular date, right? So if I go back into my data here, I can see how the dates are written. x1.22.20, x1.23. R doesn't allow you to have a column name that starts with a number. So R is going to automatically tack on this extra X. But really here, these are the dates, right? So our dates are really the call names of the confirmed cases from 5 to the total number of columns in the confirmed cases. So there's our dates, x1.22.20 all the way up to x3.22.20. Okay. With those dates, I want to get rid of that x. So I can use the command gsub. Gsub takes in a pattern that I want to replace, capital X. What do I want to replace it with? Nothing. Okay, where do I want to do this? Inside of the dates vector. So then dates now looks like this, 1.22.20 all the way up to 3.22.20. Make sense? Okay. R doesn't know this is a date. It's just a string to R. So we need to convert this into an actual date using the as.date command. Okay. With as.date, we can take in the dates and then we can specify the format of the dates. It's %m per dot %d dot %y. Okay. That'll convert, whoops. That'll convert the dates into actual dates in R. So this format thing here, I know that you guys probably haven't seen that much. If you just look up on good old Google, R date format, you'll get a link here that tells you basically how to convert different dates. So basically, an abbreviated word like Jan is a %D, or a full word is a %capital B. A 2-digit year is lowercase y, a 4-digit year is an uppercase Y. Make sense? So basically you can put together that you can tell R, the date looks like this combination, and then it'll read through this string and try and convert it into an actual date that R understands, given this format, right? So 1 is the month, day is the 22, the year in 2-digit form is the 20. Okay, so I'll store that as my dates. Okay, so then I have basically everything I need. I have my dates and I have my case data. My Y label can be confirmed cases or cumulative confirmed cases. My X data is, or my X lab is time. And there's my data for California, right? Nothing, 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 nothing. And then, oh, wow, we have a bunch of cases. Questions?
That's when the tests became available, right?
Yeah.
One of the issues that I was having with that data was that it said that there were multiple levels and that those levels were actually still in the vector, even when you convert it to numeric. When you do as numeric, even then I was still having issues.
It might
So I
be
struggle.
It might be with the dates, but that shouldn't have happened. I'll take a look at your and get back to you on that, but that shouldn't have happened.
No, I figured it out, and yeah, you'll see, but I worked around it, but I was having that issue, and I was converting a lot of, well, you'll see. Never mind.
Okay. So I tried to avoid that for you guys by adding this additional command here, string as factors equals false, when we're reading in the data, so that'll make it so that R doesn't actually try and do some memory saving, so it'll keep everything as characters. Okay, but the really tricky things here were the dates, this part, and the second part, which is actually just realizing that, yeah, I want a row of data, but that row of data is really a matrix. So I need to convert it into a numeric in order for me to plot out the data. Okay, so this is just the data for California, right? Okay, and we can make this a line by specifying the type as a line. That's the data for California. Really, though, we have a bunch more rows, a bunch more states. We can add on those lines using a for loop for I in 2 to n row, or 2 to length states, or state rows, lines, dates. We'll grab the ith case data and we'll plot that out, and we'll give it a color of equal to I. All right, so then there's every state's data. Okay, so basically, once you write everything, or once you create a vector that has all the states rows, like I did here, 101 to 149, you can just iterate through. You can just loop through and plot out each of those as an additional line. Right, then you can do things like add a legend. Maybe in the top left-hand corner, you'll give the names equal to, or the legend will actually just contain the states that I've written up here. And the colors will be 1 to the length of states, because I just gave each color the ith color. And we'll give it a line type of 1, and we'll make the size equal to 60% of its normal size. And if we highlight and run all of that together, there we go. Right, we have all of the states on top of one another. And here you can do some more formatting, because here it looks like the peak is 30 for some reason, which is, oh, that's why I didn't highlight California's data. The peak is 1500. I mean, it looks like New York's data is even worse than that. So really we could actually extend the Y limits on the graph. Y lim equal to C, 0 to, I don't know, 10,000. Right, and there you can see really how bad it is in New York right now.
This isn't a big deal, but I think, didn't you ask us in the exam to differentiate for like each state the number of deaths and then recovered, and you know what I mean? So you'll have 9 or 3 per state.
Yeah, so this was for the cumulative confirmed cases, right?
Oh, okay, so you have to do, okay.
So I just copied it, and now I'm gonna paste it. See how it says confirmed here?
Right.
I'm going to replace that with deaths. There we go. So those are deaths. So the deaths are much lower. So here I set this limit to 1,000. Maybe we can do 500. There we go. That's still too high, 100. So the death rate or the mortality rate is still pretty low. Most estimates I've seen place it at between 3.5 to 4.5%.
No, I thought we were comparing each state by itself.
You could do it that way too. Totally fine.
I think that was the question, though.
Okay, sure. I just got lazy.
Or I mean, maybe I did it a whole wrong, but I thought you were doing California versus itself, all three lines and different colors for blue line for confirm.
Yeah, you're right. Use it.
Yeah. Okay.
You can do it that way too.
Yeah, I'm with the twos on that one. I thought the same thing.
All right, you're fine. Okay. Another way of doing this, by the way, is in log form. Okay. That is, rather than have just a cumulative number of cases like this, what you can actually do instead, take the log of the number of cases plus 1, because 0, the log of 0 is minus infinity. Okay. If you plot the log, that actually shows you the growth rate of the number of cases over time. So we can make that 5. Right? So the difference between logs, the difference in logs is actually approximately the same as a percent change. So you can imagine it like this, log of x, which is a continuous time variable. So imagine I have log of xt, right? If I were to take the derivative of log of xt, so log of xt, the derivative of log of xt with respect to time. Okay, what's the derivative of a log?
One over x.
Yes, so it's going to be 1 over whatever's in the inside, right? 1 over x of t multiplied by the derivative of the inside with respect to time, right? Or that's just the way you take derivatives of logs, right? 1 over whatever is inside the log thing times the derivative of the inside. Yeah? Okay. The derivative of log of xt then with respect to time is 1 over xt times how xt changes with respect to time. Okay, well in a discrete case, that's basically just saying x of t minus x of t minus 1 over x of t, right? That's how xt changes over time. It's xt, whatever its previous version was, subtracted it out. It's approximately equal to that, okay? Which is why I'm saying if you plot it out in log terms over time, it's essentially showing you the growth rate over time. Okay, that's an enormous growth rate over time. Okay, we're talking like doubling here over and over and over again. Make sense? Okay. With the next question, I wanted you guys to just take the data for California, Oregon, and Washington and combine it with the data for Montana, Wyoming, Colorado, and New Mexico. So basically exactly the same steps we did up here. But then just add them all together and compare the difference in the average change. Okay, and what did you guys find when you did that? For the last problem, what did you guys find?
West Coast is higher.
West Coast is higher. Yes. Okay, and I asked you guys to try and explain or report and discuss your results. Okay, not just the math, think about why there may be a difference. Why was there a difference? Why do you think there's a difference between the West Coast results and the Midwest results?
Population density.
Population density. We're a lot closer to one another on the West Coast than we are in the Midwest because the land is way more expensive here, right? Okay. What else?
Some of the actions that were taken, kind of the delay in the response, I guess, might have been.
I think they're more delayed in the Midwest, but sure.
Oh, yeah.
Yeah, it's like number of tests. Like
Number of tests. Sure. That's another thing that's at play here in the background, right? There's way more tests available on the West Coast than there is in the Midwest. So by default, it looks higher here.
We're also the hub for tourism, so both coasts are the
Travel
ones
more to
that
the
are.
hubs. You have your ports on the hubs, on the coasts. Right? All of those things play a role in trying to explain the difference. So I just wanted you guys to just, abstract a little bit. Yes, the math will tell you West Coast is worse than the Midwest. Sure. Okay. Why? Because when you're thinking about why, that's actually how you go from basically doing a simple t-test to formulating a regression. You're trying to then piece together the data to help you explain the difference. Okay? Okay. We've been going here now for how long? Like almost 2 hours. Okay. Let's take a little break because I need to run to the restroom. And then we'll pick back up and we'll talk about how to actually model diseases. Sound good? Okay, so we'll pick back up in 10 minutes.
Okay.
Hey Sam, I think the sandwich thing.
Yeah. Which thing?
Is like you need to take the absolute value before you run the square root.
I'll take a look at it. That shouldn't be the case. I'll take a look. Because it should always be positive whenever we're taking the variances anyway.
I don't know, but I have the same problem, so I took the absolute value before I take the square root.
Okay, I'll take a look. All right, I'll be back in 10 minutes. So they're tracking everyone's locations. They're basically an aggregator. So they're buying data from like Candy Crush. They're buying data from Google Ads. They're buying data from all these different companies that ask you for your location.
Oh.
Or they ping where your network is and they'll get a rough idea of where you are. Okay, so I take it everyone's back now. So over the little 10-minute break, I solved our problem with the white standard errors. But in case you guys didn't get a chance to open it, this is that unicast data I was talking about. So again, they're just data aggregating, and you can literally see like state by state, are people actually moving as much as they used to, which is kind of cool. This is one of the coolest things I've seen. Okay, so going back to the white standard errors. I know it's like a lot to keep jumping back and forth, but basically the problem is solved. You have to zero out the non-diagonal terms in the variance covariance matrix to do the white estimator. That's it. So that's what we were missing. So the bread is still X transpose X inverse. The variance covariance matrix epsilon prime, that's here. Residuals dot producted with the transpose of residuals. Okay, this generates a square matrix that's n by n. On the diagonal, it contains the squared terms, or the variance of the residuals. Off the diagonal, it contains the covariances. With the white estimator, we assume those covariances are 0. So we can take the we can multiply the variance of the estimator by the diag of the variance of the estimator, which is basically just an identity matrix, and it'll zero out everything that's off the diagonal. So then you can plug in that into the meat, and you'll get your white standard error. I'll post this all on Canvas, but the solution is there. It gets the exact same results as you get from the sandwich package. Okay, So that was kind of the midterm, right? It was a way for you to practice reviewing all the assumptions we've covered, reviewing the ideas of estimators, reviewing how to derive everything for all the different estimators we've covered, and to actually practice implementing them and creating some simulations to show their properties. Right, and then the last question was talking about this crazy thing of COVID that just came out of nowhere and is spreading like crazy, right? So there, it's basically like data manipulation. So today, for the rest, I thought this would take us quite a long amount of time, so we only have like 30 minutes left. So I wanted to introduce, it doesn't have anything really to do with econometrics. It kind of does have something to do with econometrics, but it kind of has absolutely nothing to do with econometrics whatsoever. And that's this idea of basically modeling how diseases spread. Okay, the reason why I want to cover this is it's a good way for you guys to practice writing code for simulating differential equations or to simulating how something evolves over time. And that's really useful when you start getting into things like time series analysis. All right. So this is the introduction to econometrics class. In your later on classes, you're going to learn how do you model stuff over time. And we're going to do that a little bit in this class, but given the scope of things, we're probably not going to have that much time to dig really into it. So I figured this would be a nice way to introduce the idea of modeling stuff over time. Okay, so today I uploaded for us the latest lecture 5, which has inside of it, go away Zoom thing. Which has inside for it, okay, I can't jump to the lecture, which has inside of it this COVID-19 SIR models. Okay, were you guys able to download that?
Yep.
Yeah. Okay. Well, anyway, if you're watching the screen sharing, here it is. Okay, so SIR models are a way that epidemiologists track the spread of a disease. Okay, so SIR models stand for susceptible, infectious, recovered models. Actually, I'm going to send you guys a really cool video really quickly. That actually is what inspired me to write this lecture, because it's something that you guys are capable of doing as well. So, okay, so I sent you guys all a YouTube video you can watch on your own time. But the YouTube video kind of captures the essence of what we're going to be doing. But they have really cool graphics. Okay, so with these SIR models, we can track how a disease basically transmits throughout a society. You start off, this is like a very baby or introduction version of an agent-based model, if you've heard that terminology before. Okay, so we're going to assume that there's some people in our world, and those people can basically live in 3 separate stages. They can be susceptible, that is, they haven't received the disease, they're not immune to the disease, and they're at risk of contracting the disease. Okay, so that's category 1. Category 2 is the infected people, those people that have already been hit by the disease, right? And they're currently carrying it, and they're able to actually spread that disease to other people. Okay, so that's category 2. Category 3 is those that have recovered. Okay, and by those that have recovered, I mean those are the people that have been hit by the disease and are no longer able to transmit the disease. Okay, the word recovered here I have in quotes because the word recovered does not mean, you know, they're out like running 10Ks. It means they're not able to transmit the disease anymore. Okay, if someone dies, technically, they recovered from the disease. They're not able to spread it anymore. Okay, or you can consider those as recovered. If you don't want to imagine that because it's unpleasant, you could say, you know, those people that are recovered just become immune to the disease and they're no longer able to transmit it. Okay, so there's 3 categories. Those that are susceptible, don't have the disease, can get it. Those that are infected, they're carrying the disease and can spread it. And those that have recovered, which is they're no longer able, they basically fall out of the society. Okay, they're already free, they're immune. Does anyone have any questions about the setup? 3 categories. No, pretty clear? Okay. Okay, we're going to model this as basically a system of equations. So this is a story, right? There's these 3 categories of people and they can transition from one state to another state over time. We want to model the dynamics of how that transition can happen. Okay, so we're going to do that by basically saying there's this total population of people that exists at time t that is susceptible. We're going to call them S of t. That's this term here. Okay, so S of t is a total population of people that is susceptible. The actual number, like 10 million, 20 million. Okay, the number of people that are infected by the disease we're going to denote by I of t. And the total people that have recovered from the disease, that have recovered from the disease, we're going to denote by R of t. Okay. If those are the 3 categories of our population, then the total population at time t is going to be N of t, which is going to be S of t plus IT plus RT. I'm going to ignore growth on any of these variables. So I'm just going to assume there's this existing population. So really you can drop the t. Okay. The population is going to stay constant over time, which means those people that recover, they're not dying, right? They're just staying in the population as a separate zone. And we're not assuming that those are susceptible or reproducing, so like not a lot of corona babies happening, right? So it's just the population has remained constant over time and the people can be transmitted across the 3 different categories. Okay, so again, we can represent that as 3 different differential equations. So right now, we talked briefly about the idea of taking a derivative of a variable with respect to time. And I said that if it's a log variable and you take the derivative with respect to time, it's like you're taking a percent change, right? I told you the derivative of xt with respect to time is basically just how xt changes over time. Yes? Okay. With these sort of equations, what we're going to do is basically write down equations that describe the laws of motion for the susceptible population, the infectious population, and the recovered population. That is, we're going to write down equations that describe how those 3 different numbers change with respect to time. Okay, and it's going to be a very simple toy model that allows us to do that. So I'm going to stop sharing this screen. I'm going to share my iPad screen instead. Okay. So again, we have 3 different categories, right? We're going to talk about first, we're going to describe how does the susceptible population change over time. Add a new drawing. Okay. So we're going to first look at the susceptible. This sucks. Whatever, close enough. Okay, that's our susceptible population. The equation we're going to use to describe how the susceptible population changes over time is going to be, paused.
Jason? Sorry, yeah. I don't know if anyone else is having this issue, but
No,
I can't
see anything.
Drawing.
Can you see it now?
Yeah.
Okay. Hold on a second. You see it now? Still fine?
Yeah, now it looks, I can see it. The word susceptible.
Yes, that is the word susceptible. And now that word is gone. Okay. So we have a certain fraction of the population that's susceptible. We're going to assume that at any given time, there's going to be a certain fraction of our population. We're going to denote by beta S of t, I of t. Okay. These are the people that can go from being susceptible to being infected at time t. Okay, so we're going to call this thing ds of t dt. That is, the way the susceptible population changes over time is a certain fraction is going to leave, minus beta s of the population is going to leave and become infected. Okay, the rate at which that can happen is directly related to actually the number of people that are infected. So as the number of people that are infected grows, as I of t grows, this whole term is going to grow, right? The entire thing is going to grow. Okay. So really, the thing that's actually going to be driving basically how many people are transitioning from being susceptible to being infected is going to be governed by beta. Okay. And beta is basically a way of capturing the degree of contamination. So how likely it is for you, given an interaction with someone else, to actually contract the disease. Make sense? Okay. So the way I've written this in the notes is you can really think of decomposing beta into two terms. You can think of decomposing beta as it being equal to really these two terms, alpha and p. Okay. So imagine this. Every day you go out and you interact with a lot of people. I'm sure you guys have been thinking about this now more often, right? Like, how many people do I actually like see in a given day? Okay. So we can say alpha is the number of people you see on a given day, right? So maybe you see like 50 people per day. Okay. You have a lot of interactions with those people. I mean, yeah, you may only see 50 people, but like you might share some food with them. You might give them a handshake. You might give them a hug. You might. Every single one of those interactions, there's some degree that you're going to be contaminated. Okay, that degree of contamination we're going to call P. We're going to call P, right? The total number of people you interact with, we're going to call alpha. Okay, now just thinking about this, what are we all doing right now?
Meeting class over Zoom.
That is very
we're reducing alpha.
Interactions. Yes.
Reducing alpha, yeah.
Yeah, we're reducing alpha. We're reducing alpha. P is kind of constant, right? That's just the part of the disease. How likely is it to spread given given a contamination or given any interaction? Okay. Now, the second component is going to be, go away. The second component is going to be basically how likely it is, or what are the dynamics of those people that are infected, right? They're not just going to stay infected forever, okay? So we can write down an equation that describes the laws of motion for the people that are in the state of infection. They can't go from being infected back to being susceptible, right? There's no way to go in that direction. But over time, some of those people are going to get better. They're going to get healthier, right? They're going to transition out of being susceptible or out of being infected. So over time, there's really two things happening to the population of infected people, right? So again, how does the degree of infected people change with respect to time? That's how you'd read this, right? So I know it looks fancy, but it's just, right? That I looks like crap. There we go. Better. So how does the number of infected people change over time? Okay. Well, we know that there's a certain fraction of people that were susceptible that are becoming infected, right? That comes from the first equation, right? So those people that were susceptible and are now becoming infected are going to become, they're going to increase the population of the total class or total group of infected people. So this is literally just the first equation is plugging directly into here. But now it's positive, not negative. Okay. Now, that's how the infected population increases. The infected population is going to be decreasing as there's certain people that become healthy over time. So we're going to subtract out the fraction of the population that recovers, gamma, of the infected population at that time. Those are the people that are going to become recovered. Okay, so at any given time, the number of infected people is increasing by the fraction of susceptible people that become infected. So S became I is this term. And the second term is I became R. That is, they were infected and then they became recovered.
Consider the dead in the second one.
Yes,
right?
we're going to call recovered people as basically just not spreading the disease anymore. Make sense? Okay. Well, our recovered population is going to change over time. By simply the number of people that were infected that became healthy. Okay, so basically there's really two main parameters that are driving this model, right? And those two main parameters are basically beta and gamma. Beta is telling us how frequently people that were susceptible are becoming infected. This is annoying. There we go. New drawing. Okay, anyway, the number of infected people. So there's basically only two parameters, right? Beta is driving the number of susceptible people that are becoming infected, and gamma is driving the number of infected people that are becoming recovered. Those are the two key parameters, right? Okay, in epidemiology, those two terms, the ratio of them are called R naught. So R naught, I'm sure you guys have maybe seen in the news, basically tells us how dangerous or how contagious a virus is. Okay, the higher the R naught, that is the higher the ratio of beta divided by gamma, the higher this number is, the more contagious. Okay, and you can think of it like this. If beta is way bigger than gamma, that means a lot of people are becoming infected and not a lot of them are recovering. Right? Or the converse, if gamma is really big and beta is really small, then not a lot of people are becoming infected and they're recovering. Those that do get infected are recovering really quickly. Right? So then it's not a very contagious disease, or it's not a very dangerous disease. Okay. Another way of thinking about gamma actually is also relating to the speed of recovery. Okay. You can think of gamma as basically the fraction or the likelihood of you going from infected to recovered. Okay. 1 over the likelihood of you going from infected to recovered is basically how long it takes for you to recover. Okay. Does anyone know off the top of their head how long people are taking to recover from COVID right now? How long
I think it says weeks.
2 weeks, right?
Yeah.
Everyone's
2
saying
weeks.
roughly 2 weeks. Okay, the number I've been seeing around is about 14 days.
Yes.
Okay, with about 14 days, that implies that gamma is equal to 1 over 14. Okay, and this
Like
thing is,
gamma would be a fraction?
yeah, it's a number less than 1. So you can really think of it like the likelihood of you going from infected to recovered.
Yeah.
Sir. Hello, hi, Sam.
Sorry?
Here we assume that the total population remains static the entire.
Yes, so I'm keeping the population fixed at n. So actually the formal definition of R naught actually has something to do with the population as well. So the actual formal definition for R naught, the degree of danger associated with the disease or degree of contamination of the disease is really n times beta over gamma. Okay, and if you do a quick Google search, which I did a little earlier, you can look up how scientists quantify the intensity of an outbreak, like COVID-19. Okay, so this was a really nice description that I'll share with you guys right now in Zoom. That walks through how to think about basically the degree of contamination. How do I send you guys? I can stop that share. There. Are you guys getting all these messages?
I'm asking here.
Okay. So take a look at that article and it'll help explain sort of this idea of spreading or measuring the spread of a disease. Okay. But basically, we have, if I were to go back and share my laptop screen, we basically have a disease that's basically just, or you can describe the dynamics of any disease really in terms of these 3 equations, right? Which is pretty straightforward. The dynamics of the susceptible population, the dynamics of the infectious population, the dynamics of the recovered population. Okay. Now, these are equations that you can actually mathematically derive the properties for, right? And that'd be like what you did in your differential equations class. In a time series setting, though, the way you would traditionally approach this is you would actually just write some code to simulate what these equations look like. Actually, that's what you would do in differential equations as well, right? So in differential equations, you'll look at, okay, how does this thing change over time? What are they called? The phase transition lines or the phase lines? What we can do is basically write some code to actually simulate this model. And then once we have some code to simulate this model of how a disease can spread across a susceptible population to an infected population to a recovered population, we can see how simple things like imposing greater social distancing actually has an impact on the spread of the disease. Right? So is all of this stuff that we're doing pointless to stay at home, or does it actually have an impact? Okay, so let's actually do that. So let's write a simulation where we're going to assume the total susceptible population is 100,000 individuals, right? Or you can really think of this like there's 100, there's 8 billion people on planet Earth. Okay, and we can start off with a very, very small fraction. Not 1%, it's much lower than that. We can start off with a very small fraction of people that are actually infected. We'll start off with 10 people, so 10 out of 100,000 that are actually infected. We'll assume that if you're infected, it's going to take you roughly 14 days to recover. Okay, and for our baseline, we're going to assume that the average person has about 50 interactions per day, and for every single one of those interactions, there's a 1 in 30 million chance you contract the disease. Okay, which is a pretty small number, right? You can walk to the grocery store, you're fine, as long as that guy doesn't cough in your face and you happen to walk into it like right at that exact moment, right? Okay. So given these parameters, there's a lot of typos in here. you can actually figure out what the R naught is of the disease. So again, that's that epidemiological spread, the article I sent you from the University of Michigan. I hope you guys check it out. Given these parameters, we're actually giving an R naught of about 2.3. Most people are estimating R naught at about 2.5 to 3, or 2 to 4 for COVID-19 as this degree of spread. So these parameters are actually pretty reasonable to try and capture how quickly COVID-19 spreads. Okay, so here's what we're going to do. We're going to actually write some code to simulate the model. Okay, so I'm going to show you guys basically how you can go about taking a system of equations, or coming up with a story, writing down some equations for it, which is what we've done so far. Now we're writing some code to actually simulate those equations and see what falls out of it. Okay, this is actually how a lot of stuff is done in macroeconomics and how a lot of stuff is done in finance for like asset pricing. Okay, so we're going to start off with a susceptible population at time t. So we're going to create a variable s of t that's just equal to 100,000. Okay, I'm going to clear everything. So S of t I'm going to define as 100,000. I of t I'm going to define as 10. R of t, the initial the recovered population at time t, I'm going to call it 0. These are just going to be the starting values. Okay, what we're going to do is add on to these vectors. So we're going to append another number here, which shows basically how S of t is changing over time. Okay, we're going to find gamma as 1 over 14. So gamma is going to be this really tiny number, 0.07. There's a 7% chance of you going from infected to recovered on any given day. We're going to define the average number of interactions a person has as 50, and the likelihood of you contracting the disease from any one of those 50 interactions or 50 people you meet with as 1 in 30 million. That'll give us a beta of this really, really, really tiny number. Okay, or an R naught of roughly 2.33 if you combine the population, the beta, and the gamma together. Okay, we're going to simulate that system of equations, this thing, all three of these, for 200 time periods. Okay, basically 200 days. And what we're going to track is how many people transition from being susceptible to being infected to being recovered. Okay, and we'll be able to see how rapidly that happens. Okay, so we're going to create a variable called days to simulate, it's just the number 200. Now, to simulate those equations, it looks really complicated, right? Fancy, ordinary differential equations. It's really not, okay? All those equations are just summarizing how a variable changes over time. That's it. How a variable changes over time is basically its previous value plus the change. That's it. That's its value in the next period. Previous value plus the change gives us the value in the next period. Francis, do we assume the population at t equals 1 equals population at tn static? Yes, the population is going to be fixed, static. Okay? Now,
okay, thank you.
Yeah, what we're going to do is simulate the changes in the susceptible population at time t. Okay, so the changes in the susceptible population at time t are given by this equation, minus beta s of t, so minus beta times the current, the actual population size at that time, times the number of infected people at that time. Okay, so that's going to be the change at the time. There it is, exactly that, minus 1 times beta times I of t at iteration I, that's time t, this time, times the actual size of the population, or susceptible population at that time. Okay, we're going to store that change inside this variable dst dt. We're going to do the exact same thing for the infected population. Beta times I of t at time step I times S of t at time step I minus gamma times I of t times I. It's exactly what this equation is, right? Here it's a plus beta, here it's a minus gamma. And the recovered change is just going to be gamma times the IT. Okay. If we want to actually track how the levels are changing over time, you basically take the existing value at that time and then you add in the change. Make sense? So this was the current susceptible population at that time. Here I'm adding in the change. Current infected population at that time, add in the change. Current recovered population at that time, add in the change. Okay, and then we're going to append that to the vector RT, and we're going to replace RT with the appended version of itself. So then we're just tracking how the susceptible population itself is changing over time. Okay, make sense? Any questions? If I asked you to do a homework problem on this, you'd be able to do it? Yay, okay, sure. Okay, so once that code is running, basically you end up with a vector S of t, which tells us the size of the susceptible population over time. We start off with a susceptible population of 100,000. Over the course of 200 days, the susceptible population falls to 12,894. Okay. The infected population, on the other hand, grows from 10, and it peaks at having basically 10,000 people, or more than that, almost 20,000 people being infected. Okay, that's 20% of the population. So if I were to highlight and run all of this code together, it'll basically plot out the 3 lines that summarize how the susceptible population changes over time, how the infected population changes over time, and how the recovered population changes over time. Okay, the susceptible population falls from 100,000 to 20,000. That means 80% of the people in our model get infected. Okay. The degree at which people are getting infected actually accelerates and decelerates over time. Okay. Up to a period about 100, the amount of people getting infected is accelerating. After period 100, the amount of people getting infected starts to decelerate, starts to slow down because there's just not as many people you can infect anymore. Everyone's already been infected.
And you're assuming that the population is constant, right?
Yes.
It's also.
Okay. But here's what's nice. Once you have this in code, you can modify it. You can add on population growth. I can add on another element to the susceptible population. I can say the susceptible population doesn't just shrink. I can also say it's growing by a constant factor of 0.02 times STI. For instance, that'll allow me then to simulate additional population growth. I can inject new people into the society. Okay, that'd be a huge growth rate, by the way. It'd be 2% per day, right? Okay.
Yeah.
So we can also do other things. So like here, I kept the parameters of the model fixed. I said on average, throughout this entire 200 days, people's interactions is at 50. I can cut that interaction in half by telling everyone to stay home by shutting down the entire economy. You laugh, that's what we're in, right? That's our situation.
I mean, if you put it that way.
That's literally it, right?
We're saving lives.
Yeah, well, yeah, exactly.
By shutting down the economy.
It's the same thing, right?
What is that number? What is that 100? Like in mathematical terms? So there's a middle. It looks like a mean of that red of the infected.
So it just falls out of the equations. It's part of where it's because of the dynamics that IT and ST both enter inside of this equation. So it's nonlinear. Here. Inside this equation, both ST and IT play a role in how IT is going to change and how ST is going to change. Does that make sense?
Got it. Thank you.
Yeah. Okay. Actually, I think I'm running late for my other class. So here's what I'll leave you guys with. We can take that exact same simulation, but we can add in this additional if statement. If the days to simulate, so if iteration I exceeds a certain number, let's say 60. So let's say the virus has been spreading for 60 days. After 60 days of the virus spreading, we decide, tell everyone to stay home. Okay, so we respond with a lag. The virus has been spreading. After 60 days, we tell everyone to stay home. Some people listen to us, some people don't. On average, the interaction rate falls from 15 people per day to, let's say, 30 people per day. We can see how that's going to have an actual impact on the disease. That's what's happening here. We're setting alpha to 30 rather than alpha being 50. So from periods 1 to 60, alpha is going to be 50. After 60, there's going to be a discrete cut where it's going to be dropping to 30 interactions. Okay. We can then see how the number of interactions or how the number of cases changes over time. It's a drastically different scenario. It's entirely different, right? There was 80% of the population gets infected. Now it's 40% of the population gets infected. How many of you guys have heard the term flattening the curve? Okay. This is what we mean by flattening the curve. The speed or the number of people getting infected, rather than having this huge like hump shape in it like this, you flatten it out by minimizing the degree of social interactions. And that's what leads us to this flatter curve. Okay, so there's a reason why we're all being locked at home. I was hoping we could model it mathematically like this. It's relevant to econometrics because it shows you, well, one, how to simulate equations over time. And two is, we're forced to interact over a webcam. So this is why. Okay. I urge you guys to all take a look at the video link I sent you. Which one? The YouTube video. It's a really cool way of going through the SIR models, like with really nice visual interactions. Cooler than anything I can do. So I really recommend you guys look at that. And I'll try and write down a homework assignment for you guys to toy around with those models and maybe calibrate them and play more with the COVID data, just to keep practicing your econometric skills. Okay. Now, this lecture has been recorded. I said that at the very beginning, right? So if it's all right with all of you guys, I'm just going to post it on YouTube. I might edit out a couple of things here and there. And then that way your classmates that are in different time zones they can see it. Is that okay with everyone?
Yes.
Sound good.
Okay.
It's okay.
Cool. All right. Well, if you guys have any questions, email me or email Uni anytime. I'll still try and do office hours. It'll just be Zoom office hours, and we'll go from there. Okay?
Sounds good. Thank you.
All right. I hope you guys are all keeping safe. Take care.
Thank you.
Thank you, Doctor.
Thank you so much.